Okay, as we talked about in the last section, there's two ways to look at an integral. One way is looking at an integral as an antiderivative. The other way is what we're going to look at this time. We're going to look at the integral as the areas underneath the curve. And these seem like very different things, but in the very final section of this chapter, we're going to learn the fundamental theorem of calculus, and it's going to show that there's actually a connection between these things, between the antiderivative and the areas underneath the curve. Okay? So I'm going to introduce this idea with just a simple example. So the function that I'm going to be interested in is just very simple. F of x is equal to x squared. And I'm going to consider this on the interval, let's say from, we'll say from 1 to 3. Okay? And so, if I drew a picture of this, right, here's y equals x squared. Let's say 1, 2, 3. So the area that I'm interested in here is this area underneath the curve. Okay, so you know we have areas for finding, or formulas for finding the areas under rectangles, triangles, even circles, even some curved regions, but nothing for like a parabola like this. Okay, so the idea here is we're going to estimate this area under the curve between 1 and 3 by using rectangles. And so what I'm going to do is let's use 4 rectangles. So what is this area? That's the big question. So I'm going to use 4 rectangles to estimate this area. Now this procedure always made really good sense to me, because if I were to find this area, the best thing I could do is, you know, use some rectangles to find the area. So this first one I'm going to do, let me erase that. The first one I'm going to do is I'm going to use a they call it a left-hand sum. A left-hand sum. So I'm going to draw a nice big picture. And let's say this is 1 to 3. Okay, so the left-hand sum means, so I'm going to use, we're going to use 4 rectangles. And they're going to be equal size. Okay, so each rectangle is going to have a width, and sometimes they call this, I'm going to use delta x here. Each one, so the width would be 3 minus 1 divided by 4. So the idea here is we're getting the length of this, and I'm going to take the interval from 1 to 3, which has a length of 2, dividing it into 4 pieces, so each piece is 1/2, right? So we have these. We got 1, 1.5, 2, 2.5, and 3. So there's 4 sub-intervals on this overall interval from 1 to 3. Okay? Sometimes they call each one of these intervals like a partition. So you got 1 to 3. So sometimes they use this. And so this is the, you know, the absolute value is like the distance. You're not concerned about sign or whatever, the distance, and P is a partition. So this is a way of saying the length of the partition. Like you're partitioning that interval up into 4 subintervals, and then this symbol, the absolute value of p, is another way of saying. But delta x is like the distance. Kind of that delta x is going to relate to like the d of x in our integral symbol, is what you're going to find out. Okay, so here's the idea then. The left-hand sum means I'm going to use the left endpoint for the height of each of these rectangles, okay? So this is like the left endpoint. So this would be my first rectangle. This would be my second rectangle. This would be my third rectangle. And this would be my fourth rectangle. Okay, and what I'm going to do is find the area of each of these 4 rectangles. I'm going to add those areas together, and that's going to give me an estimate of the area underneath the curve. It won't be exact. In fact, this will be an underestimate, okay, because each of these rectangles are underneath the curve. Now, a left-hand sum will not always be an underestimate. It depends on the curve. Okay, if the curve is shaped different, then it could be an overestimate. Okay, so it's not that the left-hand sum gives you an underestimate, the right-hand sum gives you an upper estimate. It does in some cases, but not in all cases. But in this case, I'm going to get an underestimate. Okay, so I'm going to say, and this is just a notation that you can use. S with the little 4 subscript. That means a sum, a finite sum, a sum of 4 rectangles. Okay? Now each rectangle, the height of the rectangle is the value of the function. So like we have 1, 1 here. This is 1.5. And I think that's 1.5 would be like 1.5 squared. Is that like 2.5? Let me look. 2.25 or 1. I think my calculator's getting low on batteries. 1.5. I should have charged it. Yeah, 2.25. 1.5 is 2. Oop, I'm not going to get it in here. You know what I'm going to do? I'm going to make a table. Instead of trying to put it in here, let's do this. Let's make a table with my x and then f of x. So we got 1, 1.5, 2, 2.5. And so these are going to be like the height of the rectangle. So 1 is 1. This is 2.25. 2 is 4. And I think this is 6.25. Let me do 2.5 squared. 6.25. Okay. So this will be the height of each rectangle here. So the width of each rectangle is just the length of the delta x. The width of each rectangle is 1/2. Okay? And so for my sum, to get the area of one of these rectangles, I'm going to take the height of the first rectangle, which is 1, times 1/2, because that's the width. For the second rectangle, the height is 2.25. 2.25 times 1/2. And that'll give me the area of the second rectangle. And then here, the height of this rectangle is 4 times 1/2. And then finally, the area of this last rectangle is going to be, the height is 6.25 times 1/2. And so then what I can do is I can add these together. So 1 times 1/2 is just 0.5 plus 2.25 times 0.5 plus 4 times 0.5 plus 6.25 plus 0.5, or times 0.5. And So then I get an estimate, 6.75. Okay, and that would be an estimate of the area, okay? And it would be an underestimate, so the actual area is a little more than that. Okay, so now what I want to do is I want to do a right-hand sum and show you what that would look like. And we're going to use 4 rectangles again. So we got like 1, 2, 3. So got these midpoints. And so now what I'm going to do here for my right-hand sum, and we could make this table again if I wanted to. You have 1, 1, or I don't even need the 1 here, but 1.5, 2.25, 2, 4, 2.5, and this will be 6.25, 3, and that's 9. So now what I'm going to do here is I'm going to take the right endpoint of each rectangle, and then I'm going to add up those rectangles like this. And what you see here is that these rectangles here, when I add up those 4 rectangles, I'll actually get an overestimate of the sum. Okay? So my S4 in this case would be the sum of these 4 rectangles. And so I actually don't need that one. Just this one here would be, the height would be 2.25 times 1/2 plus plus 4 times 1/2 plus 6.25 times 1/2 plus 9 times 1/2. Okay, and so now I'm going to add these up together. So maybe I'll bring this down. I'm going to delete that first one, and then I'm going to add this last one, 9 times 0.5. I get 10.75. 10.75. And that's going to be an overestimate. Okay? So that means the actual area is between these two. 6.75, and we'll say area, and 10.75. So that's the underestimate and overestimate. The actual area is in between those two. Now there's a way of getting a better estimate here, and this is called using the midpoint rule. Let's see if I can actually draw this out. So the point of this midpoint rule, I'm going to try to make this a little bit bigger. We'll say this is 1, 2, 3. Okay. So then you have 1.5, 2.5. And so now, instead of using the left point or the left endpoint or the right endpoint, I'm going to use the midpoint of each of these intervals as the height of my rectangle, like this. So this rectangle will go up to the midpoint over that. So over each interval, what you're going to do is you're going to use the midpoint of each of these as your estimate. And so these would be your intervals. But the height now is going to be the midpoint of each interval. And that should give you a better estimate because you're not getting all, I mean, some of it's below, some of it's above, but it's kind of leveling out the estimate. So what are my midpoints, my 4 midpoints here? Well, let's see if we can get them. This would be like 1.25 and then 1.75 and then 2.25 and then 2.75. Okay, and again, in between each of these is 0.5, right? So the width is still 0.5. It's just I'm taking the midpoints of the intervals. Okay. So let's see. I'm gonna find what these are here. Boy, what did they do before they had calculators, huh? 1.5625, and then 3.0625. .0625 and 7.5625. So for each of these rectangles, these are going to be the height. So I'm going to write this underneath here. So my S4 in this case, using the midpoints, would be 1.5625 times 1/2 plus 3.0625 times 1/2 plus 5.0625 times 1/2 plus 7.5625 times 1/2. And then let's go ahead and add these up. 1.5625 times 0.5 plus 3.0625 times 0.5 plus 5.0625 times 0.5 and plus 7.5625 times 0.5. And what I get here is 8.625. And then that should be a better estimate. And that is kind of in between those two. I don't know if it's halfway between those two. Probably isn't exactly. Let's see what I get when I add these two together and average them. So the halfway mark is like 8.75. Halfway between those two. So you get something kind of close to that. But this is the midpoint rule. And this is going to give you an even better estimate. Okay, but now there's an even better way of getting an estimate using these sums, and that is by using more rectangles. So instead of splitting this up into 4, you could split up into 8 rectangles. You could split up into 10 or 16 or 32 or 64. You could keep doubling each time. And the more rectangles you get, the better estimate the better your estimate is going to be. And you see this a lot in pictures of text, and you could see it would be a lot of work to do a whole bunch of little rectangles, especially if you used all 3 rules. But you can you could do it by hand. There's also software that actually, I bet you could go online and type in left-hand sum, right-hand sum, or what these are actually called, there's a name for it, Riemann sums. So if you looked, software like Riemann sum calculator or something like that in Google, you would actually find something that could do all this work for you. But this is the concept. This is the idea. You're finding areas underneath a curve by dividing that area up into multiple rectangles, okay, and adding the area of each rectangle up. The height of the rectangle is the value of the function, these here. The width of each rectangle is usually the same. When you do a Riemann sum, I think they are the same. And it's just the upper endpoint minus the lower endpoint divided by the number of rectangles. Okay, so in other words, if you were going to do your thing from A to B and you wanted n rectangles, then your delta x would equal b minus a over n. Okay, and this would give you the partition. That would give you this number, and then you could find your endpoints, whether you want the left endpoints, right endpoints, or even the midpoints, and then you could construct the sum, and then you can get the area underneath the rectangle. Or I'm sorry, you can get the area underneath the curve using the rectangles.